Okay, let's move on to confidence intervals. We know that for an unbiased, normally distributed estimator, our guess is going to be within two standard errors of the truth 95% of the time. We already talked about why that is, but now we're going to exploit this a little bit further, because actually we can kind of flip that around and say, let's just shift this little kind of a bracket over so it's centered at the truth. Okay, or sorry, centered at our estimate. And now we're going to say, well, if we center that at our estimate, then the truth is in that same interval, is in that interval 95% of the time. The thing is that now this interval is random, right? Because our guess is random. So if we try this again, we might be over here, right? But because our guess is in this gray area 95% of the time, that means that this endpoint is going to be a kind of, or rather this dotted line is going to be within these endpoints 95% of the time, as long as this thing is within the gray area 95% of the time. So we can kind of move that around. I'm just giving you different examples. Okay, here's a case where it doesn't fall in here, but what our claim is that this only happens when this is in that tail, or this tail, which should only be happening 5% of the time. It's going to be a very rare event. So this zone around the estimate is called a 95% confidence interval. How do we build it? We have to take whatever estimate we get, and we have to add roughly 2 times the standard error of that estimate, and subtract roughly 2 times the standard error of that estimate. So let me, again, just give you an idea of what this looks like. These intervals cover truth 95% of the time. So like here, right, where we are kind of shifting around saying our estimate is different every time that we repeat the experiment. Okay, let's just look at that. So if we had 20 data sets that we were repeating the experiment, and we were calculating the value of our estimate every time, and then based on that estimate, we were adding and subtracting 2 times the standard error to build our confidence interval. Our estimates and confidence intervals might look like this. So here, if the true value of our estimand is this here, which of course generally we don't know, but if we did, we could plot it, and then we could look at our confidence intervals, and we would see that 19 out of 20 would cover the true value. But every now and again, we're going to get 1. In this case, 1 out of 20 is 5%. So 5% of these will not cover the truth. So that is the meaning of a 95% confidence interval. The confidence interval is random, right? Because the estimate is random. So different data set, different confidence interval. But over all of them, if you look at all the confidence intervals, 95% of them are going to cover the value of the truth, which is not changing. Okay, this is fixed. We don't know it, but it's fixed. So we can actually have a look at this in a simulation. So here I have this set up where I am generating each data set has 100 observations, and within each of them, it's simple data generation process. X is a normal random variable with a given mean. Here it's 0. And what I'm interested in is the population mean of X. So it's 0, right? That's the population mean, but I don't know. I just have my data of 100 samples. So my estimator is this. I take my data and I take the sample mean of X in the data. And what I'm doing here is just generating my sample mean estimate for 10,000 different data sets. And now what I'm going to do is I'm taking the actual standard error of the estimates across all those 10,000 replications. Now, this is something I could never do in reality, right? Because I don't have my 10,000 replications. But I'm just showing you if I could do that, if I knew the real standard error of the estimates, how would I construct the confidence interval? Well, here's how I would do it. I can have my estimates, and I'll take the left endpoint of my confidence interval will be the estimate that I got minus 2 times this standard error, which reflects like the true standard error. It's this sigma, right? The true standard error of the sampling distribution. And then I have the same thing plus 2 times that standard error. And now I'm computing this thing called cover. I'm just asking, since I have the true mean, I have A and B, I can just ask how many, for this data set, did my confidence interval that I constructed contain the true mean? This is the true population mean, right? And now I'm going to plot that. So here's my, I think I'm only plotting 100 runs out of the 10,000 that I did, but I'm plotting the estimate that I got and then the confidence interval. And I've highlighted in pink the iterations where the confidence interval did not contain the value 0, which is the true mean. And what you can see is that 1, 2, 3, 4, 5, 6, so 6 out of 100, very close to 5%, don't contain the value 0. And so this is indeed a 95% confidence interval as advertised. Now the problem is that I have this value here. Like the way I built this confidence interval, I used the true standard error that I got from actually taking the standard error of the sampling distribution. I can't do that. In reality, I don't have the sampling distribution, but we know how to solve that problem. All we need to do is get the estimated standard error and put that in here, and we're good to go. So, this is just showing you that, yeah, we get 95% coverage, roughly. So we don't know the standard error. That's bad. So we got to estimate it from data. So here, it says it's magic, but it's not. You actually already know how this works. We know that the standard error of the true standard error of the sampling mean is the standard deviation of the measurement divided by the square root of n. We know that's the true standard error. So all we need to do is we need to estimate what that is from the data. So we, instead of using the true standard error of x, we use the sampling standard error of x here. So that's what we're doing. This is my estimated standard error. I can do this within each iteration. And now I'm going to do the same thing that we did before. So now you can see I'm not using the true standard error. I'm using the standard error that I'm estimating from the data within each iteration and doing the same thing. And you can see that still our coverage is pretty good. Here in this set of 100, we got 4 out of 100 that don't cover the true value. So this is, again, a 95% confidence interval. So let's add to our general process for inference. Because before we were just getting to the point where we had this estimated standard error, but I wasn't really telling you what to do with it. I was just telling you that if it's smaller, that's better because you're more confident. But now we can actually build this confidence interval, which is something that people consider to be an interpretable way of visualizing or giving information about the sampling uncertainty of your estimate. And you can do this if your estimator is asymptotically normal. It's very easy. You just take your estimate and then you add and subtract 2 times standard error. But there are more general procedures as well for other estimators if it's not asymptotically normal, but you know the sampling distribution or whatnot. The general process is the same. You just construct some interval where mathematically you can show that the truth will be in this interval 95% of the time under the given assumptions. And that statement should be understood as the truth is fixed. The interval will cover the truth 95% of the time. The interval is what's random. All right, so let's do a little problem here. I want to know how variable the doses Z are for people receiving stem cell transplants. So that's what we have in this data set here in the medical data package. And maybe I want to know the population variance of this because I'm thinking maybe there's subpopulations where people are getting like really high doses and other subpopulations where they're getting low doses. I just want to know, is that the case? Or is it relatively homogeneous? So I want to estimate that population variance, but I don't have the population. I have a sample. And so I can estimate that. Let's just do that first, and then we'll get into this next part. So let's just see what's in here. These are my variables. Asking about population variance of the cell dose. So I think it's this thing, TNC dose. Okay, so what's the variance of the TNC dose? So a according to this sample, the variance in the sample is 18.7. Now, I'm not in this domain. I don't know if this is relatively big or relatively small, but if you were, you would perhaps have some idea if this indicates a large degree of homogeneity or not. But of course, this is just the sample variance. This is not the population variance. So I want to know how close is this to the population variance? How close do I think it might be to the population variance? And for that, we need to calculate the sampling, the standard error for this number. So by doing math, I've actually been able to show that the asymptotic variance of the sample variance estimator is this thing. Gamma minus sigma to the fourth, where gamma is expected value of z minus the mean of z to the fourth. This is the fourth centered moment. That's another way of saying this. And then this is just the variance of z, the sigma squared. So this here is the variance of z squared, and this is the fourth centered moment. So, okay, the problem is we don't know what these numbers are, so we have to use the data to estimate them. So let's construct a plug-in estimator for the asymptotic standard variance. So we have this fourth centered moment. It's the mean of TNC. Let's just rename it for convenience, so we can see what we're doing. Okay. So we have the mean of z minus z to the fourth. Okay. So this is my plug-in estimator for this gamma. And then we need a plug-in estimator for the sigma to the fourth. That's just the variance of z squared. Like that. So let's do it. Okay. So this number is the asymptotic this is the asymptotic variance of the sample variance estimator. So if we want to get to I could put asymptotic standard error. If I want to get the standard error, I just need to take the square root of that. I need to take that divided by the square root of n. And what is n? It is n row of this thing. So let's see what it is. Okay, so my estimated variance is around 20, but the estimated standard error is pretty big, right? So, judging from this, okay, so let's build a confidence interval. So yeah, this is my estimated population variance of the dose. This is my estimated standard error. So if we wanted to build a confidence interval, we would just do like this. So let's call this estimate. We have our asymptotic standard error estimated and our estimated standard error. And if we want a CI confidence interval, it's going to be the estimate minus 2 times C. Something like this. So CI. Okay, so there we go. So what this tells me is that we really have no idea. Okay, what the variance, the population variance of this thing is, because this is a very wide confidence interval, and in fact, this negative number, since what we're estimating is a population variance, it actually can't be negative, right? It has to be a positive number. So this is a case where the asymptotic approximation, or the normal asymptotic approximation, doesn't really hold for finite samples. Because if our sampling distribution of the estimator, it cannot actually have negative values. So that's just kind of telling us that the approximation may not be very good. But regardless, it is a case where we don't have a lot of certainty, right? our estimate was around 18, right? But this is telling us, well, okay, we could have very well gotten another data set where the estimate was 100, right? So we don't really know a lot about what the population variance is in of the TNC dose. So these are some conceptual questions now. Let's say we have an estimator that's asymptotically normal, but it's actually biased. If we make 95% confidence intervals, will they actually cover the truth 95% of the time? So let's look at this picture here. I think maybe this is the easiest one. So here, the assumption was that this is the truth, right? But what if the truth is somewhere else? What if the truth is here, right? This is the truth, and this is just the expected value of our estimate. So now this is this is the bias, right? Question is, do these confidence intervals cover the truth 95% of the time? And the answer is absolutely not, right? Absolutely not. In this case, very few of them cover the truth. So what we're saying is a 95% confidence interval is not. It's a lie, right? This is not a 95% confidence interval. This is like a 1, 2, 3, like a 3 out of 20, roughly a 10% confidence interval. That's not very useful, right? If I'm telling you the truth is in one of these, is inside of these intervals 10% of the time, and I give you an interval, well, it's very likely it's not in that interval, right? So that's not great. So the point is that the validity of these intervals depends on a lot of things. It depends on whether your estimator is biased. If your estimator is biased, or it has a large bias, they're not going to be very good confidence intervals. If the way that you estimated if your formula for the standard error, right, getting from here to here, if this required some assumptions that are not true, then when you estimate it, this thing is not going to reflect the actual sampling distribution of that. And so maybe your standard errors will be much smaller than they need to be. And so this guy, which otherwise would have covered it, does not cover it. So confidence intervals can be wrong because your formula for the standard error is not accurate. In this situation, it relied on some assumptions about the data generating process, which are not true. Or it could be wrong because you messed up the way that you're estimating it, right? Maybe you just coded the plugin estimator wrong. You put something squared when it should have been something to the fourth or something like that. But that's kind of that's simpler, right? That's just like an error that can be fixed. The conceptual things to know about is like, okay, you messed this up, or this is not unbiased. Have to do with the assumptions that you're making about whether something is biased, whether something is really the true asymptotic standard error. And the next question here, let's say that we have an unbiased estimator with a known and symmetrical sampling distribution, but it's not normal. What do we have to change to get 95% confidence intervals? So I think the logic is to look at the picture like this, right? Okay, for normal distribution, we know that the estimate falls in this zone within kind of two standard errors of the truth of the mean of this distribution 95% of the time. But what if our sampling distribution is not normal, right? Maybe it's something that looks like this, okay? Well, how do we build a confidence interval? Well, we just follow the same logic. We just find whatever region, let's say it's this, so for here it seems like 95% of the mass might be, I don't know, like from here to here, right? We find whatever region has 95% of the mass, and then we just figure out how far we need to go to get there, right? So whatever this number is, from here to whatever this distance is, let's call it k. That's what we need to know. So this is, we can figure out whatever k is, if it's two standard errors, if it's 1.5, if it's 5, whatever. We just need to figure out what that is, and then that's what we need to add and subtract from this to make the this kind of logic apply, where we can just kind of shift that interval to center it at the estimate, And here, the only thing that changes is that instead of my 2 sigma, I just have k, whatever that thing is. So hopefully that question helps you understand the logic of the construction of the confidence interval a little bit. All right, this is fun. Confidence intervals, a lot of this stuff, the statistics, when you learn about it, it's just kind of given to you from on high. Like, why are we doing it like this? What is why do people use confidence intervals, and where do they come from? And it's not like it's like in the Old Testament, okay? It isn't like Confucius came up with the confidence interval. These things are actually incredibly modern. All of statistics is incredibly modern for the most part. I mean, like the general ideas of, like densities and things like that, sampling, that stuff's kind of, maybe 300, 400 years old. People were formally studying that. And before that, people were studying, games like probability games and like dice and gambling and stuff in more informal ways. But like real modern probability and statistics is, about 100, 120, 150 years old, roughly. And the confidence interval in particular, again, it's not like something that people have forgotten the origin of. Like, we know where it came from. It came from this paper, okay? And this was written in 1936, so less than 100 years ago. I mean, I used to think that's a long time ago, and the older I get, I'm like, that was yesterday, okay? And it was the guy who wrote this paper, Jerzy Neyman, and Jerzy Neyman was here at Berkeley. I mean, when he wrote this paper, he was at University College London, but he spent most of his career actually at Berkeley. And if you go over to Evans Hall, you can go up to the 10th floor, and there's a conference room in there where it's got a bunch of his stuff in there. Like, you can see his shit, like his protractor, like his papers, all this stuff. It's there. Like, this dude invented the confidence interval, okay? So it's pretty wild how recent this stuff is, and that it was invented by actual people who were here. Like, there are people still on this campus who you can go talk to who knew this guy. Okay, that's just wild. Anyways, just wanted you all to know that little bit of trivia, that like history is real and that we're a part of it.